Black holes don't suck. That sentence alone sounds wrong, almost offensive. Every image you've ever seen tells you the opposite. Swirling disks of fire, matter screaming inward, stars torn apart and stretched into glowing strands, entire galaxies feeding a central darkness. Even the language conspires against you. Event horizon, point of no return, cosmic vacuum cleaner. Every word suggests violence, hunger, inevitability. So when someone says, black holes don't suck, it sounds like a trick, a technical loophole, a physicist hiding behind definitions. But it isn't pedantry. It's a doorway. Because when you truly understand why black holes don't suck, you don't just fix a misconception about black holes, you uncover something much more profound, a completely different way of understanding gravity, motion, and falling itself. Black holes are not cosmic monsters that break the rules of physics. They are what happens when the rules are followed all the way to their logical end. Black holes are not failures of gravity. They are gravity behaving perfectly. And once you see that, your intuition about space, motion, and even danger itself will never be the same. Let's begin where all understanding of gravity truly begins. With falling, drop a ball, it falls. Drop a rock, it falls. Drop anything near Earth's surface, and it accelerates downward at about 9.8 meters per second square. This is one of the first facts of physics ever measured carefully. Galileo rolled balls down inclined planes and discovered something shocking for his time. Objects fall at the same rate regardless of their mass. Heavy or light, they fall together. Gravity is democratic. That idea alone overturned centuries of intuition, but it was only the beginning. Because once you understand falling, you can understand the heavens. Now ask a question that seems almost childish. Why doesn't the moon fall? The moon is above Earth. Gravity pulls downward, so why hasn't it crashed into us after billions of years? This question haunted thinkers for centuries. The moon was clearly influenced by Earth. It raised tides. It moved predictably, but it never fell. Then Isaac Newton had his quiet, revolutionary insight. The moon is falling. It's just missing. Imagine standing on a high cliff and throwing a stone sideways. The harder you throw it, the farther it travels before hitting the ground. But the Earth isn't flat. It curves. Throw the stone fast enough, and as it falls, the Earth curves away beneath it. The stone keeps falling and keeps missing. That is an orbit, not hovering, not floating, falling forever. The moon is falling toward Earth at the same time it is moving sideways fast enough to never hit. This one idea, continuous falling, collapsed the distinction between the heavens and the Earth. Apples fall. The moon falls. Planets fall. Same motion. Same physics. Newton didn't stop there. He asked how gravity weakens with distance. By comparing planetary motions, he deduced the inverse square law. Gravity decreases with the square of the distance. Double the distance, gravity becomes 4 times weaker. Triple it, 9 times weaker. This wasn't philosophical speculation. It was brutally testable. The moon is about 60 times farther from Earth's center than we are. According to the inverse square law, gravity there should be 3,600 times weaker. Newton calculated how far the moon should fall toward Earth in 1 second under that weaker gravity. The result matched observation exactly. This was astonishing. 2 completely different phenomena, a falling apple and the orbit of the moon, were suddenly revealed as expressions of the same law. This is what real understanding looks like. Not description, but unification. Now let's push this idea forward. Imagine replacing Earth with something much more massive. Say, the sun. If you were far away, nothing would seem unusual. Gravity would feel stronger, but stable. Planets would orbit just as they do now. Now compress the sun, keep the mass the same, but shrink its size. What happens? The gravitational field near the surface becomes stronger. The escape velocity increases the speed required to leave forever. On Earth, escape velocity is about 11 kilometers per second. On the sun, it's about 618 kilometers per second. Still finite. Still comprehensible. Now compress the sun further. Shrink it without changing its mass. Escape velocity rises. And eventually, something remarkable happens. The escape velocity reaches the speed of light. 299,792,458 meters per second. At that point, even light cannot escape. That critical radius is called the Schwarzschild radius. And when an object's mass is compressed inside that radius, a black hole forms. Not because gravity becomes magical, not because new forces appear, but because space-time itself becomes so steeply curved that every possible future path leads inward. This is where intuition fails and mythology begins. People imagine black holes as sucking machines, as if they reach out across space and pull things in, as if they are more aggressive than other objects. They are not. Here's a simple but shocking fact. If you replaced the sun with a black hole of the same mass and kept Earth at the same distance, Earth's orbit would remain unchanged. Same gravity, same motion, same year, nothing would suddenly be dragged in. Because gravity depends on mass, not on whether that mass is a star or a black hole. This is the first major shock. Black holes don't suck more than stars. They only become dangerous if you get very close. And that danger has nothing to do with suction. To understand what really happens near a black hole, you must abandon another deeply ingrained intuition, that gravity is a force that pulls. In Einstein's universe, gravity is not a force in the usual sense. It is geometry. Mass tells space-time how to curve. Space-time tells matter how to move. Near Earth, space-time curves gently. Objects follow those curves, which we experience as falling. Near a neutron star, space-time curves steeply. Near a black hole, space-time curves so extremely that familiar notions of up and out lose their meaning. Imagine space-time as a landscape. Earth is a shallow valley. A neutron star is a deep pit. A black hole is a cliff that never ends. Once you step too far, every direction forward leads down. This brings us to the event horizon. The event horizon is not a surface. It is not a physical wall. It is a boundary in space-time. Outside it, there exist paths that lead outward. Inside it, all possible future paths point inward. Cross the horizon, and the future no longer contains escape, not because you are pulled back, but because out has ceased to exist as a direction in space-time. This is why nothing escapes, not because it is dragged back, but because the geometry allows no outward future. This also explains why black holes do not vacuum up the universe. From far away, space-time curvature is mild. Objects follow stable orbits exactly as they do around any massive body. There is no reach, no hunger, no pull beyond what mass dictates, only geometry. Now let's address what actually kills you near a black hole. It is not gravity itself. It is tidal forces. Your feet are closer to the black hole than your head. Gravity is stronger there. The difference stretches you. On Earth, tidal forces are tiny. You don't notice them. Near a stellar mass black hole, they become lethal. You are stretched vertically and compressed horizontally, a process physicists grimly call spaghettification. But even this is not suction. It is space-time curvature changing faster than your body can adapt. Here's where things become truly strange. If the black hole is massive enough millions or billions of solar masses, you could cross the event horizon without noticing anything special. No tearing, no instant death, no dramatic moment. From your perspective, nothing remarkable happens at the horizon. You simply continue falling. But from the outside, something very different appears to happen. You seem to slow down. Your clock ticks slower. Your image freezes at the horizon, fading and reddening. You never quite cross. This is not illusion. It is relativity. Time itself flows differently near extreme space-time curvature. The event horizon is not where things end. It is where perspectives diverge. And now we reach the deepest misconception of all. For decades, physicists believed black holes destroyed information, that anything falling in was erased forever. That would violate a core principle of physics. The universe does not forget. Stephen Hawking complicated this picture by showing that black holes are not truly black. They emit faint radiation, Hawking radiation, and over immense timescales, they evaporate. This raised a terrifying question. If a black hole evaporates completely, where does the information go? The answer is still being debated. But what we now know is this. Information is not destroyed. It is encoded, scrambled in subtle correlations at the horizon. Black holes do not break physics. They force it to reveal deeper layers. So let's return to the beginning. Black holes don't suck. They don't hunt stars. They don't vacuum space. They don't violate physical law. They are the most honest objects in the universe. They take gravity seriously. They show us what happens when space-time curvature becomes extreme. They are not monsters. They are teachers. Newton showed us that falling explains the heavens. Einstein showed us that falling is geometry. Black holes show us what geometry does when pushed to its limit. And even there, at the edge of the abyss, the universe remains coherent, lawful, beautiful. The next time you see an image of a black hole, remember this. Nothing is being dragged screaming into a cosmic drain. Things are simply following space-time where it leads. And where it leads, eventually, is not chaos, but deeper understanding.